All right. Now I want to show you just some worked problems. You probably don't understand this much at all at this point, so maybe by doing maybe 3 more problems, you'll start to get a feeling for it. All right. Now, there are so many terms in here. If we don't do multiple practice problems, you're just going to feel lost. So you probably feel lost right now. That's okay. Let's get to it. All right. So let's look at 31.3. I'm going to get my board here. 31.3 in your book. So you could try and race me. It says a series RLC. Notice it doesn't matter if you say RLC, LCR, CLR, whatever. We've got a function generator. All right. It's a series LRC, whatever. Doesn't matter what order we put things. Right. We could put the resistor first if you want. Generally speaking, I like to make sure the resistor, at least one end of the resistor, is connected here. And typically, if I know where ground is in a circuit, I like to make the resistor touch ground and the function generator touch ground. All right. That just makes it easier to measure voltage across the source and current without grounding issues. Okay, we're told V source as a function of time is V naught sine omega t, where omega is 9.549 radians per second. And we know V naught is equal to 100 volts. Furthermore, we know resistance is 1.00 kilo ohms. Capacitance is 20.0 microfarads. And inductance is 3.00 millihenries. All right. It says figure out the resonance frequency. All right. So resonance frequency is not omega. Omega naught is the resonance frequency. That's 1 over the square root of LC. And in this case, it's not clear if they wanted angular frequency or regular frequency in hertz. So let's just get both. All right. So either one of these could be called the resonant frequency. If you want to use radians per second, we'd use the upper one. If we want to use the function generator, we might talk about this number. All right. So in this case, I'm just going to plug it in. All right. And so maybe I'll do it like this. 3 times 10 to the minus 3 and 20 times 10 to the minus 6. I would actually punch this in if I were you. Get used to flipping stuff around. So 3e negative 3 times 20e negative 6. And then I'm going to square root that. And I'm going to 1 over it. So I got 4 crads. Kiloradians. All I did was shifted 3 decimal places, right? So crads. All right. Part B, determine the phase angle for this circuit. I don't want to think too much, so I'm just going to get to work. Phi is tangent inverse. I'm using the equations on page 200. If you recall, page 200 is where it is in my book. There's a bunch of equations there. I'm going to use the standard one. If you recall, this came from this picture here. This is given on your exam equation sheet, where this side of the triangle was R, this side of the triangle was Z, the total impedance, and this side was the difference between the capacitive and inductive reactances. Well, in this case, wait a minute. I need to know what XL and XC are. Well, I happen to know that's omega L minus 1 over omega C all over R. And I want to leave this way. So keep in mind, if we have the capacitor dominating the circuit, we'll get a negative phase angle. A negative phase angle, if you recall from Eli, the Iceman, right? If the inductor dominates, we get a positive phase angle. Voltage source peaks before current. If the capacitor dominates, the current peaks before the voltage, we get a negative phase angle. All right, more on that in a minute. Let's get a number for this phase angle. So plugging in the numbers, oh man, maybe I'll do these up top just so I don't lose them. XL is omega L. Punching that in, what was omega? It was, it's not this. This is omega naught. I almost grabbed the wrong one. This is our operating frequency. That's what we need for X sub L. This is the resonant frequency. That just tells us which term is dominating. So 9.549 times 3e negative 3, I get 0.02865 ohms, something like that. X sub C, that's 1 over omega C. There it is. So that's 20 e negative 6 times 9.549. And then I gotta, let's see, I need to 1 over that one, not square root it. Whoa. So we can see this is clearly capacitively dominant. Do you agree the inductor here makes almost no difference in the circuit at all? Right? Again, if we're at a very low frequency, the inductor, even though it's a coil, acts a lot like just a straight wire. Because the flux is not changing that rapidly, we don't get much inductive reactance. Okay, a small amount of ohms associated with the inductor. Whereas on the other hand, if we're changing the current very slowly, right? Think about this, divide this by 2 pi, that's about 1 time per second, approximately, right? The capacitor is charging up every second. And so it's this huge amount of resistance, even more than the resistor itself. This is clearly capacitively dominated. Well, now, since I have these numbers, I can actually punch in and find the phase angle right here. So we could actually ignore this. Right? It's negligible. It's off in the 6th decimal place. So if I wanted to, this is actually something approximately equal to negative 5236 ohms. Actually, we could use kilo ohms because the resistance was 1.00 kilo ohms. So it's basically tan inverse of negative 5. Oh, yeah. All right. I forgot to write tan inverse there. You might be saying, where's the minus sign coming from? Right, it's 0 minus 5,000 because XL is effectively 0 in this case. Obviously, if it was non-zero, you'd punch in the numbers. We see the kilo ohms drop. The phase angle is, so I can divide that by negative 1,000. All right, and then tan inverse of that. I get 79.19 degrees. Now, as we discussed earlier, and this is negative. I get a negative phase angle. Negative phase angle. I can use this equation to help me out. Negative phase angle means this term's bigger. That's what gives rise to the negative phase angle, the capacitive dominating the circuit. Capacitance dominating the circuit. Now, just in case, I guess I could convert this to radians if I need it. So to convert that to radians, what is it? I want pi radians over 180 degrees. So if I multiply that times pi, divide by 180, negative 1.382 radians. So, all right, just using that conversion, just to clean things up a bit, maybe I'll write that below. All right. So we've got the phase angle in degrees, we've got it in radians, we're ready for the next part. All right, there's our conversion. What's the next part? Total impedance at this operating frequency. All right, well, so in this case, maybe I'll try and squeeze that in right here. I know that Z is the impedance, that's the square root of R squared plus XL squared, or XL minus XC quantity squared. All right, it's essentially the magnitude of the hypotenuse here, the size of the hypotenuse. Well, when I plug that in, again, in this case, XL is negligible, so it's basically 1 kilo ohm squared plus the quantity negative 5.236 something squared. So I'm just going to punch in the numbers here. You could try and race me to it. The 5.236 x squared plus 1, then square root that answer. I got 5.331 kilo ohms. As a note, I know I'm making this video without you students present right now. So if I do, remember the numbers in the solution, if you want to just follow along with them, hey, those are going to be right all the time. And so here, there's a chance I might type in a number wrong or something. So if there is a discrepancy between what you see on my board and the solution manual, trust the solution manual. I've probably just typed in a number wrong or something. That said, I don't think we've made any mistakes yet. All right. So now we've got that. We want the power. Well, what I'm going to do is I'm going to look at the table of formulas or look at my equation sheet, right? Somewhere on there. I see there's one that says power average equals I squared RMS R. Oh. And we don't maybe know what that is yet. So maybe we should talk about that. So let's go over to new board. Okay. We want to know power. This is part C. And we see that it's IRMS. And we haven't talked what that is yet. Just writing down all the different formulas I've got for it here. I'm working off the back cover now. IRMS, VRMS, cosine phi, or the one I tend to like to use, like that. Okay, so what does this mean? Well, the short version is IRMS means I root mean square. Okay, well, what does that mean? Let's say I look at the current as a function of time. The current as a function of time looks like some kind of sine wave. Well, if you square that, that's going to get rid of all the negatives. And now I don't know if the height's going to get taller or shorter. Basically, that depends on whether the number is bigger or smaller than 1. So don't worry so much about the height. Just accept the fact that when you square it, both of the bumps are going to be above there. Then we can take the average or the mean of this. Well, it turns out the mean of a cosine squared function happens to be exactly a half of the peak. All right. So the average is half of the I squared peak. Okay, that's interesting. Well, wait a minute. Wasn't I squared peak just I max was the peak value here? So this is half of the I max, or the amplitude of the current. All right, that's cool. And now what we could do is we could take the root. And so out of all this, we see that IRMS is equal to the square root of I max squared all over 2. In terms of an equation, we can come back to here. I see that I max is equal to 1 over the square root of 2 times, IRMS. IRMS is just a fancy way of saying the current amplitude. You take, this is, if it helps, I'll put it a decimal number here. It's about 0.7071 I max, or IRMS is equal to about 71% of the current amplitude. So the words IRMS, or root mean square of the current, simply is a different way to discuss the current amplitude. This is a standard way to discuss it because the power actually is this looks just like the power associated with our resistance equation. So we see that if we want to figure out power in a circuit like this, the only new thing we need to do is, oh, it's I squared R, but what do you mean by I squared R? Okay, if I want the average power delivered, the average power delivered is this IRMS. It relates to the peak in this funny way. Now I should be clear. This is average power that I just did. I'm going to read this statement again here. Right, and when I read the question again, oh, this is part D, by the way. Sorry, it's not part C. This is part D. I don't see anything clarifying whether or not we mean average power or not. Generally speaking, that's the default, but I could also get power as a function of time, and that would be I as a function of time squared times R. You could always do that as well. So in this case, I as a function of time is I max sine of omega t minus the phase angle And so obviously, if the current is fluctuating up and down, the brightness of the light bulb was fluctuating up and down. It may have been happening so quickly we couldn't see it, but yes, it was doing that. And so we see that the power would also fluctuate up and down according to this. So on a test question, I would make this more clear, but I deliberately made this sort of confusing so we would have to discuss it. And I believe this is all written up in the solutions as well to clarify. I'm not sure what I meant in this problem. It's a bad question. So again, I'm just trying to make you aware there's a difference between average power and instantaneous power, or power as a function of time. All right, in this case, I guess let's focus on the average power first, and we could always come back. This part's pretty easy. We already know omega. We already know the phase angle. The main thing here is we need to figure out the current amplitude, right? If we get the current amplitude, we can get IRMS. If we get RMS, we can get the average power or the instantaneous power. All right. Well, I know a couple of different equations. I know that the current maximum value, the current amplitude, I'm going to write that, is equal to the source voltage amplitude divided by Z. This is where students have a tendency to accidentally plug in R. I know that I max is also equal to the resistor voltage amplitude divided by R, or it's the source voltage amplitude divided by Z. Watch out. okay? If you're using the source voltage to get current amplitude, divide by the total impedance, right? This is the total voltage across all three circuit elements. We need the total impedance of all three circuit elements. If you're talking about the voltage amplitude across just the resistor, then yeah, you could divide by the resistance. In practical terms, when we were doing the circuits, this is how we displayed things on the oscilloscope. We take the voltage across just the resistor and divide by the resistance to get current. Okay. When we're doing theoretical work, generally speaking, you take the source voltage amplitude and divide by the total impedance. Well, in this case, I think we know both of these. V naught was 100.0 volts, and divide that by Z, which was 5.331 kilo ohms. And then in order to make this easier on myself, rather than plug in the kilo, I remember if I divide by kilo ohms, that's like dividing by 1,000. Well, that's the same thing as giving me milliamps. I remember kilo gives you milli. Kilo gives you milli. So if you divide by kilo ohms, you're going to get milliamps. So 100 divided by 5.331 is 18.7 milliamps. All right. Well, that's great. That's the current amplitude, right? And this is the source amplitude, right? These amplitudes are related by Z. Now, if I wanted to, I could write down the current as a function of time. Or in this case, I could write down IRMS. Well, that's just I max divided by square root of 2. All right. In this case, if I just take that and divide it by 0.7071, oh, whoops. Let me just divide by square root of 2. I get 70% of that. It's 13.26 milliamps. Now that I know this, the power is just IRMS squared times the resistance. Ooh. Well, I'm going to think a little bit. I'm going to have a milliamps squared times a kilo ohm. I should probably just convert all these. However, I can see this. This kilo will cancel one of the millis. So in the end, if I plug in the numbers, I should get milliwatts, right? Because the kilo will cancel one of the millis, but not both. Well, power is in watts, so I'll have a milliwatt. All right, so in this case, 13, well, I've got that number here. I'll just square it. Whoops. Answer squared. Whoops. Answer squared times the resistance was, wait, wasn't that just 1? The resistance was 1, I think. Yes, R was 1 kilo ohm in this problem. So that's just, it's just the answer squared. Okay. So that I get 175.9 milliwatts. All right, so that's part D. Part E, plot source voltage versus current, source voltage and current versus time on the same plot. All right, hopefully this is still working here. Man, I sure hope I'm not getting these black spots in my videos. All right. Where were we? I'm going to do it like this. And I'm going to bring up Microsoft Excel. Okay, so these are the parameters that we had. And I'm not going to write the units. We had V naught is equal to 100. And this is going to annoy me if I don't do this, so sorry. right? We had a resistance was 1E3. I'm just going to do everything in SI units. So 1 kilo ohm. The capacitance was something like 20 E negative 6, 20 micros. And the inductance was 3 E negative 3, 3 millis. All right. And let's see, we are trying to get, oh, and we found out the phase angle in degrees. Oops. What was that phase angle in degrees? Somewhere up here. Negative 79.19. We could also get the phase angle in radians, which we did already. It was, well, it's equal to, well, it's this number times 3.14159 divided by 180, right? Let's just fix up the sig figs on there. All right, so we got our phase angle. And now I think we found Z, right? We already did that. That was equal to the square root of all that stuff, but we worked it out. What was it? What was it? 5.331 E3. It was 5.331 kilo ohms. All right. So now what were we trying to do? We're trying to get time here. And so what was the, you know what I might do really quick is get a feeling for the period of this circuit. What was our operating frequency? Did it say 9? Okay. So and I'm just going to make this first column extra wide. The operating frequency or angular frequency was 9.549, I think. Yes. All right. And just so I have it, the resonance frequency was 4082. And these were in units of radians per second. All right. Apologies for the delay here. Let me get the units out of here. Okay. That way, I don't want to write the units next to the number like that. That way, if I need to use it in the formula, I've got it. Okay. So this kind of gives me an idea here what kind of time I need, right? So this is changing about 9 times. It's oscillating. Oh, geez. Let me get the frequency here. Let me move this down a couple. All right, so this is equal to this number divided by 2 divided by pi. All right, so it's flipping a couple of times a second, about once every second. This gives me an idea of how long this circuit's going to take. Or if you wanted to, I could get the period. Right, the period is equal to 1 divided by the operating frequency. All right, so now I can finally figure out my time increments, right? I see that if I go by 0.01, whoops, let's make these match, sig figs, right? The idea is I should get 60 or more points per cycle. So I'm going to do that. Now let's just go all the way out to a full second, right? All right, that's about a second. All right, so now what I can do is I know my functions, right? I know V source is V naught sine of omega t. This is omega, not omega naught. And I know my current is I max, the amplitude, sine of omega t minus phi. All right. So we're going to try and use, oh, and I guess remember we found I max already, didn't we? I max was equal to V naught over Z, which I think we have all that information. All right. So maybe what I'll do is I'll make this column blue. And I'll make this column red. Right, and these ones, I don't care. I'll change those back to black. So this was V of the source. All right, well, that's equal to this voltage with the dollar signs times sine of omega. What was omega? Do we have that? It's right here, the operating frequency, not the resonance. I do not want resonance. I want the operating frequency times the time, which is cell B6. And that's it. Obviously, the source is going to start at 0. Now I could do I, right? The current would equal, in this case, it's going to be, let's see. You know what? I'm going to do this. I'm going to go up here. We know that I max in milliamps. We had that number already. It was 18.76. I'll color that red just so it stands out. All right, so that'll save me some time. So I better put my units in here. This is in milliamps. This one is in volts. All right. This was equal to that number, that constant, times sine of operating frequency times B6, which is the time, minus the phase angle. And here we have to be careful. If I'm using radians in the omega, I need to use radians here, and Excel is using radians. So I'm going to use the phase angle in here. Notice minus and negative is going to be a positive number. Now that I have that, I'm going to grab both of these and fill that down. And I might have forgotten some dollar signs, it looks like. Ah, I did. I forgot this omega needs the dollar sign, right? I screwed up. And over here, that omega also needs the dollar signs. And so does this one. Here's a case where naming your variables probably would have been smart, right? So now we can fill these down and hopefully it does a little better. There we go. And we got way too many sig figs there. Let's just do this. All right. And now what I could do is I could make this plot. Let's just do solid curves here. And let's make these colors match. Let's go to here. Let me do this. What was series 2? Series 2 is the second one. Make that red. Oops, maybe I have to click this button. Red. There we go. Sorry about that. All right, and so we could see what's going on here. Let's go to 1 second. That's all we need. And here we can now see the phase angle and its effect. Finally, this is approximately when the current is peaking. This is when the source voltage is peaking. So that's V source max, or V naught, I guess, if you will. Right? That's peaking out at 100. The current, right? Strictly speaking, we should have a 2-axis plot here. I don't want to go into that yet. So the current was peaking right here. We have mixed units, but it was peaking at about 18 milliamps. We could obviously multiply that by a resistance to convert this to volts and have it make more sense. But right now, so this is I max, the current amplitude. And we see that this time right here, the time between the two peaks corresponds to the phase angle. And if you recall, the change in time between the peaks divided by the period should equal the phase angle in degrees divided by 360 degrees, right? Just taking ratios, right? Phase angle is how much of a 360-degree cycle. The time is some fraction of the period. All right, that's looking pretty good. That is problem 31.3. Woo! It's problem 31.3. So that's how we got those plots. And let me go to here. Whew. You know what? I should probably just make a separate video for the next problem. That way you don't have to be searching through